October 8, 1944. A testing facility outside Stuttgart. The concrete floor was stained with oil and cordite, the air thick with the acrid smell of burnt powder that clung to every surface like a memory of violence. 6 Luftwaffe armament engineers stood in a semicircle around a wooden crate stamped with faded English lettering. Property of the United States Army. Inside, wrapped in oiled canvas like a corpse prepared for burial, lay a Browning M 1919, a 4 machine gun. 30 caliber. Water-cooled. American. Hauptmann Ernst Dietrich, chief weapons analyst for the Reich's Small Arms Development Command, circled the crate with the careful steps of a man approaching something he both respected and disdained. His grey uniform was immaculate despite the workshop grime, his iron cross catching the harsh overhead lights. He had built his career on German precision, the Maschinengewehr 34, the MG 42. Weapons that represented the pinnacle of engineering excellence, where every tolerance was measured in thousandths of a millimetre and every component was machined to perfection. This American weapon had been captured 2 months earlier from a shot-down B-17 over France. The bomber's waist gunner had gone down with his ship, but the gun had survived, torn from its mount and shipped east through intelligence channels for analysis. To Dietrich, it represented everything crude about American manufacturing, mass-produced, heavy, unsophisticated, a relic from the previous war that somehow still equipped modern aircraft. Water cooling, he said to his assistant, Lieutenant Hans Müller, his voice carrying the particular contempt that German engineers reserved for obsolete technology. The Americans still use water jackets like it's 1918. Our air-cooled designs are lighter, faster to produce, easier to maintain. He gestured dismissively at the crate. This is what happens when a nation industrializes without understanding engineering fundamentals. The other men nodded, their agreement reflexive. They had all heard the stories. American factories that prioritized quantity over quality, workers who had never touched a firearm before the war, now assembling weapons on production lines like automobiles. The very concept violated every principle of German craftsmanship, where apprentices spent years learning their trade before they were trusted with critical components. Müller pried open the crate with a crowbar. Wood splintered, nails shrieked. When the lid came free, the smell of gun oil wafted up, sharp and chemical. The Browning lay nestled in its canvas shroud, its barrel jacket dark and purposeful even in stillness. Dietrich reached in and lifted the weapon, feeling its weight. 23 kilograms, nearly twice the weight of an MG 42 with comparable firepower. Barbaric, he murmured, running his hand along the water jacket's perforated casing. They sacrifice mobility for a cooling system that belongs in a museum. He set it on the examination table with a dull thud. Tomorrow we will test-fire this artifact and document its inevitable failures. The Americans may have numbers, but they lack sophistication. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Outside, the autumn rain had begun, drumming against the workshop's metal roof with the irregular rhythm of distant artillery. None of the men noticed. They were too focused on the weapon before them, too certain of their conclusions. German engineering had always meant precision. American engineering, they believed, meant compromise. What they didn't know was that this particular Browning had already fired more than 37,000 rounds through its current barrel, that it had survived combat operations across North Africa, Sicily, and 3 months of missions over occupied Europe, that the water in its jacket had boiled away and been refilled 17 times, that its barrel had been changed only twice in 18 months of continuous service. They didn't know, because the weapon showed no obvious signs of its history, No catastrophic wear patterns, no structural failures. It simply existed, patient and enduring, waiting for men who worshipped perfection to discover what durability actually meant. The workshop fell quiet as the engineers began their preliminary examination. Müller photographed the weapon from multiple angles, while another technician sketched its external features in a leather-bound journal. Every rivet, every seam, every external component was documented with Germanic thoroughness. Dietrich watched them work, his mind already drafting the report he would send to Berlin. American machine gun construction demonstrates fundamental misunderstanding of modern small arms requirements. Excessive weight. Obsolete cooling system. Inferior to German. Designs in every measurable category. He had written similar assessments before. The American Mohngarand rifle with its N-block clip that pinged when empty, announcing to every enemy soldier that the weapon was unloaded. The Thompson submachine gun with its ridiculous drum magazine that jammed in mud. The Colt 45 pistol with its primitive single-action trigger mechanism. Every American weapon he had examined confirmed his thesis that industrial mass production could never match German craftsmanship. The Browning seemed to embody everything wrong with American military philosophy. It was heavy where it should be light, complex where it should be simple, stuck with a cooling system that the rest of the world had abandoned years ago. To Dietrich, it represented the desperation of a nation that had entered the war unprepared and was trying to compensate with quantity instead of quality. Müller removed the weapon's side plate, exposing the internal mechanism. The other, engineers gathered closer, peering at the guts of the machine gun as if examining the organs of an alien creature. What they saw confused them. The components were precisely machined, not hand-fitted like German weapons, but manufactured to tolerances that suggested sophisticated production machinery. The surfaces showed tool marks consistent with automated milling, yet the dimensions appeared uniform and exact. The bolt face exhibited wear patterns consistent with tens of thousands of rounds fired, yet the metal showed no signs of structural fatigue or cracking. "The wear is even," Müller said quietly, running his finger along the bolt's locking lugs. "No stress concentrations, no deformation." He looked up at Dietrich, his expression uncertain. "Herr Hauptmann." The barrel extension shows minimal erosion despite obvious heavy use. Dietrich frowned. He had expected to find evidence of sloppy manufacturing, rough surfaces that would accelerate wear, loose tolerances that would cause malfunctions. Instead, he was looking at a mechanism that appeared to have been machined with care and assembled with precision, despite being a product of American mass production. "Production variants," he said dismissively. "We happen to receive one of their better examples. Continue the examination." But doubt had entered his mind, like water seeping through a crack in concrete. The weapon before him didn't match the narrative he had constructed about American industrial incompetence. It was heavy, yes. It used obsolete cooling technology, certainly, but it was also clearly built to exacting standards that suggested someone understood exactly what they were doing. The team worked through the afternoon, disassembling the Browning component by component. The barrel came free from its jacket with some effort, revealing a bore that still showed distinct rifling despite obvious use. The gas system, when separated from the receiver, demonstrated clever engineering that allowed for simple adjustment without requiring specialized tools. Every part they examined showed the same pattern: automated manufacturing that somehow achieved precision, usually reserved for hand-fitted components. By evening, they had spread the entire weapon across 3 examination tables. Hundreds of parts arranged in careful order, each one photographed and measured. The data they were collecting contradicted their assumptions so consistently that Dietrich found himself double-checking measurements, looking for errors that would restore his confidence in German superiority. The barrel's chrome lining was still intact after tens of thousands of rounds. The bolt's locking surfaces showed wear consistent with normal use, but no unusual stress patterns. The water jacket's welds were uniform and showed no signs of fatigue cracking despite repeated thermal cycling. Even the weapon's feed mechanism, which should have been worn and unreliable after extended use, demonstrated smooth operation when tested by hand. "The feed pawls are still within tolerance," the senior armourer reported, his voice carrying a note of surprise he couldn't quite suppress. "The spring tension remains consistent. The timing mechanisms show no degradation." He paused, choosing his words carefully. "Herr Hauptmann, this weapon appears to have been designed for extended service life rather than optimal performance." Dietrich absorbed this information in silence. Designed for extended service life, the phrase implied a different engineering philosophy entirely, not the German approach of achieving maximum performance through precision manufacturing, but an American strategy of accepting heavier weight and older technology in exchange for reliability and endurance. It was a compromise that offended his sensibilities as an engineer. Why accept obsolete cooling systems when air-cooled designs existed? Why tolerate excessive weight when lighter alternatives were possible? The German way was to push technology to its limits, to extract maximum performance from minimal materials, to achieve perfection through precision. But as he looked at the disassembled Browning spread across the tables, a question formed that he didn't want to ask. What if perfection wasn't the point? What if the Americans had built this weapon not to be the best machine gun possible, but to be a machine gun that would never quit? The rain intensified outside, drumming harder against the metal roof. Through the workshop's high windows, lightning flickered in the distance, illuminating stacks of captured American equipment waiting for analysis. Crates of Mohn rifles, boxes of .45 caliber ammunition, a Thompson submachine gun with its barrel shot out but its receiver still intact. Every piece told the same story of weapons that endured rather than excelled. Dietrich dismissed his team for the evening, telling them to prepare for live fire testing the following morning. They would mount the Prius, Browning on a test stand, feed it belted ammunition, and run it until it failed. Every weapon had a breaking point. Every design had a weakness. The test would reveal what prolonged firing did to American mass production quality. The results would confirm what German engineering already knew. But as he stood alone in the workshop that night, listening to the rain and staring at the disassembled weapon, Ernst Dietrich felt something he hadn't experienced in years. Uncertainty. The Browning had survived everything the war had thrown at it so far. Tomorrow would determine if German assumptions about American incompetence were justified, or if they had been fundamentally wrong about what made a weapon truly effective. He didn't sleep well that night. In his dreams, he heard the sound of a machine gun firing, not the sharp staccato of an MG-42, but the deeper, heavier rhythm of the Browning. The sound went on, never pausing, never faltering, like a mechanical heartbeat that refused to stop no matter what was asked of it. The morning of October 9th arrived cold and grey, the kind of German autumn day where fog clung to the ground like smoke and visibility extended barely 100 meters. Inside the testing facility's firing range, engineers worked by electric light, preparing the Browning for its trial by fire. They had reassembled the weapon overnight, documenting each step with photographs and detailed notes. Now it sat mounted on a heavy steel test stand, its barrel pointed downrange toward a backstop of earth and sandbags 200 meters distant. Dietrich arrived at 0700 precisely, his uniform pressed despite the early hour, his manner businesslike and professional. He had reviewed the test protocol 3 times the previous evening, ensuring that the procedures would stress the weapon beyond any reasonable combat scenario. They would fire in sustained bursts until the barrel overheated, then continue firing. They would deliberately use ammunition with slightly excessive powder charges to increase chamber pressure. They would test the feed mechanism's tolerance for worn belts and damaged links. The goal was not simply to evaluate the weapon's performance, but to identify its breaking point. Every machine gun had limits. The question was whether American mass production had created a weapon that would fail catastrophically under stress or merely perform inadequately compared to German designs. Müller had spent the morning preparing ammunition. 10,000 rounds of captured American .30 caliber ball ammunition, inspected and sorted to remove obvious defects. The cartridges were loaded into cloth belts using original American links, each belt containing 250 rounds. The ammunition bearers stacked the prepared belts on tables beside the firing position, creating a mountain of brass and copper that glinted dully under the overhead lights. "The cooling water is prepared," Müller reported, indicating 2 large metal cans filled with distilled water. "We have thermocouples mounted at 6 points along the barrel jacket to monitor temperature distribution. The chronograph is calibrated and positioned 3 meters from the muzzle. All safety observers are in position." Dietrich nodded his approval. German thoroughness would document every aspect of the American weapon's performance and inevitable failure. When the test concluded, he would have data to support his assessment that German engineering remained superior despite American industrial advantages. The first test sequence called for measured bursts at combat rate, 5 to 7 round bursts with 3 to 5 second pauses between them, simulating the firing pattern of a bomber's defensive position or a ground support role. This was how machine guns were typically employed in combat, conserving ammunition and managing heat buildup while maintaining suppressive fire. Dietrich personally loaded the first belt, feeding the cloth through the weapon's receiver and seating the first round against the feed pall. The mechanism operated smoothly, the bolt sliding forward with well-oiled precision to chamber the cartridge. He stepped back and nodded to the designated test operator, an experienced armourer named Feldwebel Koch, who had fired thousands of rounds through various machine gun designs. "Commence firing," Dietrich ordered. "Standard combat bursts." Koch pressed the thumb trigger. The Browning responded instantly with a sharp, authoritative bark that echoed through the enclosed range. 6 rounds. 7 rounds. The cyclic rate was immediately apparent, approximately 450 rounds per minute, significantly slower than German machine guns that approached 1,300 rounds per minute in the case of the MG-42. "Slow," Müller muttered, making notes on his clipboard. "Inefficient cyclic rate for suppressive fire." But Koch, who had trained on multiple weapon systems, noticed something else. The weapon's recoil was remarkably controllable. The heavy barrel and water jacket absorbed vibration that would have made lighter weapons difficult to keep on target. Each burst placed its rounds in a tight group downrange, the impacts visible as small dust puffs against the earthen backstop. They continued the measured burst, firing for 15 minutes. 700 rounds expended. The barrel temperature climbed steadily but remained well below critical levels. The water in the jacket grew warm but showed no signs of boiling. The weapon fed reliably from multiple belts, the links ejecting cleanly without causing feed stoppages. Dietrich watched the chronograph data with growing attention. The muzzle velocity remained consistent across hundreds of rounds, showing no significant degradation that would indicate chamber erosion or gas system problems. The cyclic rate stayed within a narrow band of 440 to 460 rounds per minute, suggesting precise timing mechanisms that weren't affected by heat or fouling. "Increase to sustained fire," he ordered. 20-round bursts, minimum pause between them. This was beyond normal combat employment, deliberately stressing the weapon's cooling system and feed mechanism. Koch nodded and adjusted his grip, preparing for the increased recoil energy that sustained firing would generate. He pressed the trigger and held it, counting mentally. 20 rounds. Release. Immediate second burst. 20 more rounds. The sound became a continuous tearing noise, deeper than German machine guns but no less deadly. The temperature readings climbed faster now. 50 degrees Celsius. 70 degrees. The water in the jacket began to shimmer with heat, though it remained well below boiling point. Koch continued the sustained bursts, working through belt after belt with mechanical rhythm. 500 rounds. 1,000 rounds. 1,500 rounds. The weapon never faltered. Each belt fed smoothly through the receiver. Each cartridge chambered and fired without hesitation. The spent casings formed a growing pile beside the test stand, brass glinting like scattered coins. The links ejected in a steady stream, clattering against the concrete floor with metallic percussion that provided counterpoint to the gun's deeper voice. Müller checked the barrel temperature probes. 90 degrees at the chamber end, 75 degrees mid-barrel, water temperature approaching boiling point. Dietrich made a decision that surprised even himself. Continue firing. I want to see what happens when the water boils. This was beyond any reasonable test protocol. Machine guns with water cooling systems were never meant to boil their coolant dry. The entire point of water jackets was to maintain barrel temperature below critical levels indefinitely. But Dietrich wanted to find the weapon's limits, to push it past its design parameters and document the resulting failure. Koch continued firing. 2,000 rounds. 2,500. The water in the jacket began to bubble audibly, steam rising from the filler cap in thin wisps. The temperature readings climbed past 100 degrees Celsius. The barrel was now operating at temperatures that would cause most weapons to experience gas system problems or timing issues as metal expanded beyond design tolerances. The Browning kept firing. Its rhythm never changed. Its feed mechanism never jammed. Round after round after round, each one chambering and firing and ejecting with the same mechanical precision as the first. The pile of spent brass grew to hundreds, then thousands of cartridges. The air filled with the smell of burnt powder and hot metal, so thick it made the observer's eyes water. At 3,000 rounds, the water in the jacket reached full boil. Steam poured from the filler cap in a continuous plume. The barrel was now operating essentially without cooling, the boiling water providing minimal heat transfer capacity. This should have been the point where the weapon failed, where excessive heat caused the metal to lose its temper and the mechanism to seize or malfunction. Instead, the Browning's cyclic rate actually increased slightly. 470 rounds per minute. 480. The weapon was responding to reduced friction as expanding metal parts created tighter clearances. Koch glanced at Dietrich, his expression questioning whether to continue. The Hauptmann nodded grimly. They would fire until something broke. 4,000 rounds. 5,000. The belt feeders developed a rhythm, replacing empty belts before the weapon could run dry. The continuous firing created a hypnotic cadence that filled the range with sound and fury. Observers began gathering at the safety line, drawn by reports that the Americans' captured machine gun had been firing continuously for over an hour without malfunction. At 6,000 rounds, the water in the jacket had boiled away completely. Steam had evacuated through the filler cap and vents, leaving the barrel operating in a dry jacket that provided no cooling whatsoever. The metal was now glowing faintly red in the dim light of the range, radiating heat that could be felt from several meters away. This was a failure condition that should have caused immediate catastrophic malfunction. The Browning continued firing. Its voice had deepened slightly as the hot barrel resonated differently, but the rhythm remained steady. 7,000 rounds. 8,000. The feed mechanism should have seized as heat conducted through the receiver and expanded the tolerances beyond functional limits. The bolt should have stuck in the chamber as the hot metal gripped the cartridge case. The gas system should have failed as pressure differentials changed with extreme temperature. None of these things happened. The weapon simply kept firing, as if American engineers had somehow anticipated that soldiers might push their machine guns far beyond recommended operating parameters and had designed accordingly. The barrel was now bright red along most of its length, glowing like a forge poker pulled from fire. Paint on the water jacket had burned away, exposing bare metal beneath. Dietrich found himself unable to look away. He had witnessed countless weapons tests, had evaluated dozens of German and captured foreign designs. He had never seen anything maintain function under such extreme conditions. The MG-42, Germany's finest machine gun, required barrel changes every 300 to 400 rounds of sustained fire to prevent overheating damage. This American weapon had just fired 20 times that amount and showed no signs of stopping. 10,000 rounds, Müller announced, his voice barely audible over the continuous firing. His clipboard hung forgotten at his side, his careful documentation abandoned in favor of simply watching history unfold. The other observers stood in stunned silence, their preconceptions about American engineering dissolving like morning fog under the relentless sun of empirical evidence. The Browning fired on, its red-hot barrel a testament to design philosophy that valued endurance over elegance, reliability over refinement, persistence over perfection. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. At 12,000 rounds, Koch's hands were numb from vibration despite the weapon's remarkable stability. His ears rang even through the protective muffs all observers wore. The pile of spent brass beside the firing position had grown so large that assistants were shoveling it into metal drums to clear the floor. The barrel glowed like molten metal, its red heat visible even in the bright electric lights of the range. Still, the weapon fired. 13,000 rounds, 14,000. The feed mechanism operated, with the same mechanical precision it had demonstrated at round 1. The bolt cycled with identical timing. The ejection pattern remained consistent, spent cases arcing through the air to land in the same rough area they had since the beginning of the test. Dietrich had stopped taking notes an hour ago. He simply stood and watched, his engineer's mind trying to reconcile what his eyes were reporting with what his training insisted should be happening. By every principle of metallurgy and thermodynamics he understood, this weapon should have failed catastrophically thousands of rounds ago. The barrel should have warped from differential heating. The receiver should have expanded beyond tolerances. The gas system should have lost timing as pressure curves changed with temperature. Instead, the Browning demonstrated something that German engineering philosophy had never prioritized: the ability to tolerate abuse that would destroy more refined designs. It was heavy because weight absorbed heat and vibration. It used water cooling because liquid coolant provided thermal capacity that air cooling could not match. It had generous tolerances because tight fits seized under thermal expansion. Every design choice that German engineers had dismissed as primitive or obsolete was revealing itself as deliberate engineering for worst-case scenarios. At 15,000 rounds, Müller approached Dietrich with fresh temperature data. Herr Hauptmann, the barrel temperature has stabilized at approximately 900 degrees Celsius. The gas port shows no erosion. The chamber dimensions remain within acceptable limits based on our measurements. 900 degrees, hot enough to soften most steels, hot enough to cause structural changes in metal that would lead to rapid failure. Yet the Browning's barrel continued functioning, its chrome lining apparently protecting the underlying steel from the worst effects of extreme heat. American metallurgists had clearly understood that combat weapons would be abused beyond their rated parameters, and had engineered accordingly. The observers began murmuring among themselves. Word of the test had spread through the facility, and engineers from other departments had gathered to witness the spectacle. Some made hushed comments about American industrial capacity, wondering aloud if mass production had somehow achieved quality that hand-fitting could not match. Others remained silent, watching the glowing barrel pump round after round downrange with mechanical indifference to the extreme conditions. At 17,000 rounds, Dietrich made a decision that would have seemed unthinkable that morning. Prepare additional ammunition. We will continue until we reach 20,000 rounds or catastrophic failure, whichever comes first. 20,000 rounds represented approximately 45 kilograms of ammunition, more than an infantry company would typically carry for sustained operations. No, single engagement would consume such quantities. But Dietrich needed to understand the limits of American engineering, needed to find the breaking point that would validate his assumptions about German superiority. Koch changed positions with a fresh operator, his arms exhausted from controlling the weapon through thousands of rounds of sustained fire. The new gunner, a veteran armourer named Schmidt, took up the thumb trigger and continued the relentless cadence. 18,000 rounds, 19,000. The barrel had moved beyond red heat into a bright orange glow that hurt to look at directly. Steam still rose from the empty water jacket, residual moisture evaporating from metal surfaces heated far above boiling point. At 19,500 rounds, something changed. The cyclic rate increased noticeably, climbing to nearly 500 rounds per minute. The weapon was losing headspace as the barrel expanded from heat, allowing the bolt to close faster and fire, sooner in its cycle. This should have been the beginning of the end, the start of a cascading failure as timing problems led to extraction difficulties and eventual seizure. Instead, the Browning adapted. The heavier bolt mass compensated for the timing change. The extraction claw's generous dimensions maintained grip on spent cases, even as chamber dimensions shifted. The gas system's over-engineered capacity delivered sufficient pressure despite changed port dimensions. The weapon continued firing as if nothing had changed, its American designers having apparently anticipated even this failure mode and built in accommodation. 20,000 rounds. Schmidt released the trigger and stepped back, his face pale with exhaustion and wonder. Silence filled the range like water flooding a basement, sudden and overwhelming after the continuous thunder of sustained fire. The barrel glowed bright orange along its entire length, radiating heat in visible waves. The water jacket's metal had discolored from temperature stress. The receiver was almost too hot to touch, but the weapon had not failed. It sat on its mount, steam rising from its surfaces, ready to fire again if called upon. 20,000 rounds without a single malfunction. 20,000 rounds without a parts failure. 20,000 rounds that had transformed German assumptions about American engineering into smoking wreckage as thoroughly as any bomb could destroy a factory. Dietrich approached the weapon slowly, his hand extended toward the receiver. The heat was palpable from half a meter away, radiating like a bonfire. He withdrew his hand before making contact, unwilling to risk burns. Instead, he walked around the test stand, examining the Browning from every angle, looking for visible damage or stress that would explain why it had stopped when ordered, rather than because it had finally broken. He found nothing. The barrel was discolored and obviously heat-damaged beyond reuse. The paint had burned from the water jacket. The wood grip handles were charred. But the mechanical components, when examined through the still-hot receiver, showed no visible failures. The bolt was in battery. The feed mechanism rested in its normal position. The extractor claw held a spent case that had been extracted but not ejected when firing stopped. Müller joined him, clipboard in hand, his face showing the same mixture of shock and growing respect. Preliminary analysis suggests the barrel will need replacement due to heat damage to the rifling. The water jacket shows thermal stress but no structural failures. All other components appear serviceable. Serviceable. After 20,000 rounds of continuous fire hot enough to glow orange. Serviceable. The words seemed inadequate to describe what they had witnessed. German machine guns required barrel changes every few hundred rounds of sustained fire. The MG-42, their finest achievement, was considered exceptional if it could fire 1,000 rounds before needing component replacement. This American weapon had fired 20 times that amount, under conditions that would have reduced German designs to molten scrap. The observers began drifting away, their conversations subdued. They had come expecting to witness the failure of American mass production, to confirm their beliefs about German engineering superiority. Instead, they had seen a demonstration of design philosophy so fundamentally different from their own that it challenged everything they thought they understood about weapon development. Dietrich remained at the firing line long after the others left, staring at the cooling browning as daylight faded outside and the range lights cast harsh shadows across its battered surfaces. The barrel had faded from orange to red to dull cherry, its heat gradually dissipating into the cold October air. But the lesson it had taught would not cool so easily. That night, alone in his office, Ernst Dietrich began writing his report to Berlin. The words came slowly, each sentence a small surrender of beliefs he had held for his entire professional life. The American Browning M, 1919. A 4 machine gun demonstrates design characteristics fundamentally different from German engineering principles. Where German weapons optimize for maximum performance under ideal conditions, American weapons appear designed to maintain acceptable performance under extreme conditions that would destroy more refined systems. He paused, his pen hovering over the paper. The next words were the hardest he had ever written in his career. This represents a valid engineering philosophy that German small arms development has failed to consider. In warfare, reliability under abuse may prove more valuable than perfection under controlled conditions. It was an admission that hurt worse than any physical wound. But as he looked at the photographs of the glowing barrel spread across his desk, at the data showing 20,000 rounds fired without mechanical failure, Ernst Dietrich understood that he had been asking the wrong question all along. The question was never whether American weapons were as refined as German designs. The question was whether refinement mattered when the alternative was a machine gun that simply refused to stop working no matter what you did to it. Outside his window, snow had begun to fall, early for October. Each flake dissolved on impact with the ground, leaving no trace of its existence. German engineering, he thought, was like those snowflakes, beautiful, precise, fragile. American engineering was the ground itself, crude, heavy, enduring. He finished his report as midnight approached, then sat in silence for a long time, listening to the old building creak and settle around him. Somewhere in the facility, the Browning sat on its test stand, cooled now to room temperature, ready to fire another 20,000 rounds if asked, ready to prove again that sometimes the best answer to engineering problems wasn't more precision, but more forgiveness. Dietrich finally understood what that meant. The Americans hadn't failed to achieve German levels of refinement. They had deliberately chosen not to, recognizing that war demanded weapons which survived imperfection rather than demanded it. In that choice lay a wisdom that German engineering, for all its brilliance, had never grasped. The snow continued falling outside, and Ernst Dietrich sat alone with his thoughts, wondering what other assumptions about the war might be as wrong as his beliefs about American machine guns had been. November 5th. 1944. The report reached Oberkommando der Wehrmacht in Berlin 3 weeks after the test, passed through multiple layers of command with increasing levels of classification until it landed on the desk of General Major Kurt Steiner, chief of Wehrmacht small arms procurement. Steiner had spent 30 years in military service, rising through the ranks by understanding logistics and industrial capacity rather than tactical brilliance. He read Dietrich's assessment twice, then called for his senior staff. The meeting convened in a conference room deep in the Reich Chancellery complex, where thick concrete walls muffled the sounds of Berlin's daily Allied bombing raids. Maps covered one wall, showing German defensive positions across multiple fronts. Production charts filled another, tracking weapon output from factories that were being steadily reduced to rubble by American and British bombers. The men who gathered around the table represented the core of Germany's military-industrial expertise, and they had come to discuss a single question. How had American mass production achieved reliability that German craftsmanship could not match? Steiner began by reading selected passages from Dietrich's report aloud. The 20,000-round test, the barrel glowing orange, the weapon continuing to function under conditions that would destroy German designs. Some of the assembled officers shifted uncomfortably as the implications became clear. Others listened with the grim attention of men who recognized that battlefield realities were contradicting comfortable assumptions. The Americans are not building weapons to our standards, Steiner said, setting down the report. They are building to different standards entirely, standards which prioritize endurance over performance, simplicity over sophistication, reliability under abuse over precision, under ideal conditions. Oberst Friedrich Hauptmann, chief of the Heereswaffenamt Small Arms Division, spoke up. With respect, Herr General Major, the test conditions were extreme beyond any combat scenario. No gun crew would fire 20,000 rounds continuously. The test proves theoretical capability, not practical advantage. Steiner nodded, having anticipated this argument. And yet our intelligence reports indicate that American bomber gunners regularly engage in sustained combat lasting hours, that their machine guns aboard B-17 and B-24 aircraft function reliably despite extreme altitude, temperature variations, and combat damage. That captured American ground forces carry weapons which continue functioning despite neglect that would render our equipment inoperative. He pulled another document from his folder, this one marked with fresh ink. This is from Army Group Center. They report that captured American weapons are now preferred by some of our frontline troops over issued German equipment, specifically because of superior reliability in winter conditions. The American weapons function when our precisely manufactured components freeze or foul. The room fell silent. The admission that German soldiers preferred captured enemy weapons struck at the core of national pride and engineering philosophy that had driven Wehrmacht equipment development for decades. It suggested that the careful tolerances and precision manufacturing that German industry took such pride in were actually disadvantaging their troops in field conditions. Major Hans Dietrich, Ernst's cousin and a liaison from the Luftwaffe Technical Command, cleared his throat. The question then becomes whether we can adopt American design principles within our manufacturing capacity. Can German industry produce weapons with the generous tolerances and robust construction that enable this reliability? Steiner's expression darkened. This was the core problem, the question that had kept him awake since reading Ernst Dietrich's report. Our manufacturing capacity is built around precision machining and skilled labor. We have spent decades training machinists who can work to thousandths of a millimeter tolerance. Our quality control systems reject components that would be perfectly acceptable by American standards. To adopt their approach would require fundamentally rebuilding our entire arms industry. He gestured toward the production charts on the wall. More critically, we lack the industrial capacity to implement such changes, even if we had the will. American factories produce thousands of machine guns monthly using semi-skilled labor and automated machinery. Our factories produce hundreds using skilled craftsmen and manual processes. We cannot compete in quantity, so we have focused on quality. But if quality means precision, that becomes fragile under field conditions, then we have optimized for the wrong variable. The discussion continued for 2 hours, circling the same fundamental problem from different angles. German engineering excellence had created weapons that performed brilliantly under controlled conditions, but struggled with the chaos of actual combat. American engineering mediocrity had created weapons that performed adequately under any conditions, including ones that would destroy more sophisticated designs. Hauptmann finally asked the question everyone was thinking. Are we losing because we built better weapons, while the Americans are winning because they built simpler ones? Steiner considered his response carefully. The answer had implications far beyond small arms development, touching on strategic assumptions about how industrial warfare functioned in the 20th century. We are losing, he said slowly, because we assumed that engineering excellence would overcome industrial capacity. The Americans understood something we did not, that in modern warfare, the side which keeps more weapons functioning in the field wins, regardless of how precisely those weapons were manufactured. He stood and walked to the wall map, his finger tracing the shrinking borders of German-controlled territory. Every front reports the same pattern: American forces equipped with simple, reliable weapons that function despite poor maintenance and harsh conditions. German forces equipped with sophisticated weapons that require skilled maintenance and careful handling. When both sides engage, the Americans' weapons keep firing while ours jam, freeze, or fail. Superior German tactical training and fighting spirit can only compensate for equipment failures up to a point. The room absorbed this assessment in uncomfortable silence. It contradicted decades of military doctrine that emphasized technological superiority as a force multiplier. It suggested that Germany's vaunted engineering expertise had led them down a strategic dead end, producing exquisite machines for a type of warfare that no longer existed. Major Dietrich spoke again, his voice careful. What does the General Major recommend? Steiner returned to his seat, suddenly looking much older than his 53 years. I recommend that we acknowledge reality. American weapons work better in field conditions than ours do, despite being manufactured to lower standards of precision. This advantage compounds their already overwhelming superiority in numbers. We cannot match their production capacity. We cannot redesign our manufacturing infrastructure to adopt their methods. Therefore, we continue producing weapons using our existing methods, while understanding that we have been outmaneuvered at the strategic industrial level. It was a surrender, disguised as pragmatism, an admission that Germany had lost the arms race before the first shot was fired. The assembled officers understood the implications. Their sophisticated weapons, their precisely manufactured components, their engineering excellence that the Reich had celebrated for years, all of it meant nothing against an opponent who had chosen simplicity and won. The meeting adjourned with no actionable decisions beyond increased emphasis on weapons maintenance and training. There was nothing else to be done. German industry would continue producing precisely manufactured weapons because it could not do otherwise. German soldiers would continue using equipment that failed under the extreme conditions of Eastern Front winters and Western Front mud. And the Americans would continue advancing with their crude, reliable, indestructible machine guns that refused to quit no matter how badly they were abused. That evening, Steiner stood alone in his office, looking out over Berlin's blacked-out streets. Somewhere in the city, factories ran through the night, producing weapons components that required skilled machinists and careful assembly. Across the Atlantic, American factories ran 3 shifts, producing weapons that high school dropouts could assemble with minimal training, weapons that worked despite manufacturing imperfections that would make German engineers weep. He thought about the Browning machine gun glowing orange in its test stand, firing round after round after round without failing. Thought about German machine guns that required barrel changes every few hundred rounds or risked catastrophic damage. Thought about all the variables that military planners considered when evaluating weapons systems: accuracy, range, rate of fire, weight, manufacturing cost. They had forgotten to adequately weight the most important variable of all: whether the damned thing would still work after a soldier had dragged it through mud, frozen it in a Russian winter, baked it in a North African summer, dropped it from a truck, fired it until the barrel glowed, and then asked it to fire another 1,000 rounds. The Americans had remembered. They had built weapons for soldiers, not for engineering competitions. Heavy weapons, simple weapons, crude weapons that forgave every sin and kept functioning when sophisticated alternatives failed. In doing so, they had won the industrial war before the shooting war had even properly begun. Steiner pulled out his own copy of Ernst Dietrich's report and read it one final time. The technical language couldn't hide the fundamental truth embedded in 20,000 rounds of test data. German engineering had achieved precision. American engineering had achieved persistence. And in the calculus of industrial warfare, persistence proved more valuable than perfection. He filed the report away and returned to his other duties, working late into the night as he always did. Outside, the air raid sirens began their nightly wail, and American bombers droned overhead, dropping ordnance manufactured in the same factories that produced those indestructible machine guns. The symmetry was almost poetic. American industry was defeating Germany in the air and on the ground, with crude, simple tools that simply refused to break no matter how hard anyone tried to destroy them. The lesson was clear, but it had come too late to matter. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.